Hello, welcome to EEE 101. Today we will discuss about Norton's theorem and maximum power transfer theorem. Both these theorems are closely related to Thevenin's theorem, which we have already learned. Let's look at Thevenin's theorem again. If we have a linear two-terminal circuit between node A and node B, according to Thevenin's theorem, this two-terminal circuit may be replaced by an equivalent circuit consisting of an independent voltage source VTH in series with a resistance RTH. Norton's theorem is similar in the sense that Norton's theorem says this linear two-terminal circuit may be replaced by a different equivalent circuit. What is the equivalent circuit in Norton's theorem? The equivalent circuit consists of an independent current source IN in parallel with a resistance Rn. So, according to Thevenin's theorem, the linear two-terminal circuit is replaced by a voltage source in series with a resistance, and Norton's theorem, the linear two-terminal circuit is replaced by an independent current source in parallel with a resistance. Although Norton's theorem was originally proposed independently as an independent theorem, it can be derived from Thevenin's theorem and source transformation theorem. In Thevenin's equivalent circuit, we have a voltage source in series with a resistance. So we can transform this equivalent circuit using source transformation theorem and obtain an equivalent current source in parallel with a resistance. So if we apply the source transformation theorem, this is the circuit that we get. Here, the value of the current source is VTH by RTH, and the parallel resistance is equal to RTH. Now, both these bottom circuits are identical, so they are equivalent. So if we consider this equivalent circuit and this equivalent circuit identical, we can argue that IN is equal to VTH by RTH and RN is equal to RTH. So these are the two relationships that we get for Norton's equivalent current IN and Norton's equivalent resistance RN. Now the question is, how do I determine IN and RN to find the Norton's equivalent resistance of a given circuit? To find IN, we will short circuit our two desired nodes A and B, keeping all independent sources active in the linear two-terminal circuit. If ISC is the current flowing through this short circuit, then this ISC is equal to the Norton's current IN. Because Rn and RTH are equal, all three different techniques that we have learned to determine RTH can also be applied to determine Rn. So again, we have three techniques to find Rn, namely case 1, special case, and case 2, which we discussed when we talked about Thevenin's theorem. Okay, now we move on to maximum power transfer theorem. In electrical engineering, we routinely transfer electric power from one location to another location. This schematic diagram describes the process in a very simple way. We have a linear two-terminal circuit and we have a load RL. Linear two-terminal circuit has produced a voltage VL across the load and a current through RL. So the load power is IL VL. So we can see that this linear two-terminal circuit is transferring electrical power to this load resistance, and these two may be located at two different physical locations. There are two primary reasons why we send electrical power from one location to another location. The first reason is to transfer electrical energy from one location to another. For example, we may have a power plant outside the city and the loads may all be located within the city. So the electrical power produced in the power plant has to be transferred to the city where all the loads are located. In the next reason, we transfer information in the form of electrical signals. Electrical signals are represented as voltages and currents. So when we want to transfer information, we transfer electric voltages and currents. A common example may be our landline telephones. Okay, so what is the objective that we should look for when we transfer electrical energy or when we transfer information? When we transfer electrical energy, we want to utilize as much energy possible as we have produced. So we can say that we want to minimize the loss of electrical energy during the transfer process. Minimizing the loss means maximizing the efficiency. So when transferring electrical energy, our guiding principle is to minimize loss or to maximize efficiency. However, the principle is different when we want to transfer information in the form of electrical signals. When we transfer information, we want that the quality of the information or the quality of the signal at the receiving end will be good. Now, why does the quality degrade when we transmit the electrical signals? Because the signals are contaminated by noise and interference, among other factors. Noise and interference affect weak signal or low power signals more. So to minimize the unwanted effects of noise and interference, if we can raise the power of the received signal, then noise and interference will have less effect on the information. So when transferring information, our guiding principle is that we want to maximize the amount of received power. That is, the power of the electrical signals at the receiving end should be maximized. This will ensure that the quality of information at the receiving end is best. Maximum power transfer theorem deals with the second point, how to maximize the amount of received power. The number one point we will not discuss in this course. It will be discussed in a future course on power system engineering. So let's focus on maximum power transfer theorem. We come back to our schematic diagram. We are transferring power to this load resistance RL from the linear two-terminal circuit. The linear two-terminal circuit can be replaced by its Thevenin's equivalent VTh in series with RTh. The load power is VL-IL. VL is the voltage across load and IL is the current through the load. Using voltage divider rule in this circuit, VL can be expressed by this expression. And using Ohm's law, RTh and RL are in series. Using Ohm's law, IL can be expressed by this equation. In this case, we are considering that our two-terminal linear circuit is fixed. If the linear two-terminal circuit is fixed, then VTh is fixed, RTh is fixed. The only variable in this circuit is the load resistance RL. So the question whose answer we are looking for is what value of RL will make PL maximum? We can vary a resistance from its minimum value 0 to its maximum value infinity. In this range, what value of RL makes PL maximum? That is what we want to find out. Okay? If I substitute VL and IL in the equation of the power PL, this is the expression we get. Remember, here VTh and RTh are constants. RL is our independent variable or the x-axis variable, and PL is our dependent variable or the y-axis variable. Okay, and our question is again this one. Which value of RL makes PL maximum? To answer this question, we will apply the maxima minima theorem that you have learned in calculus. If PL is a function of RL, as shown here, PL will be either a maximum or a minimum when the first derivative of PL with respect to RL is 0. When this condition is satisfied, PL is either a maximum or a minimum. From physical conditions, we know that this PL as a function of RL does not have any minimum. It only has a maximum. So this first derivative equal to 0 condition will identify the maximum. In the expression of PL, we have RL both in the numerator and in the denominator. Using U by V technique, we can differentiate that and we get this expression. This expression is 0 when the numerator within the bracket is 0. So from the numerator, we get this equation. This is a simple second order equation, and solving it, we find that RL is equal to RTH. That means the load will receive maximum power from the fixed two-terminal linear circuit when the load resistance is equal to the Thevenin's equivalent resistance of the two-terminal circuit. And what is the maximum value of the power? If you substitute RL in case of RTH in this equation, we find out that the maximum value of PL, which we are calling PL max, is equal to VTH square over 4 RTH. These two relationships together are known as the maximum power transfer theorem. Now, before we solve problems, let's look at the nature of variation of PL when RL is varied in a graphical manner. X-axis represents RL, the minimum value RL equal to 0. That means the load is short circuit. Zero resistance represents short circuit. And this point indicates that RL is equal to infinity, the maximum value of a resistance, and RL equal to infinity represents open circuit. When the load is short circuit, the voltage across the load is 0. So load power is also 0. We will expect that PL is 0 when RL is equal to 0. Similarly, under open circuit condition, the load current is 0. So again, the load power is 0. So at both ends of the x-axis, we get 0 load power. So how does the overall curve look like? If we show the graphical variation of PL, this is the graph that we will find. Initially, as RL increases, PL will increase, PL will reach a maximum value, and beyond that, when RL is increased even more, PL will continue to decrease and eventually becomes 0. So where is this maximum point located and what is the value of power at this maximum point? These two questions we have already answered from maximum power transfer theorem, the derivation that we did in the last two slides. So the maximum power occurs when load resistance RL is equal to Thevenin's equivalent resistance of the two-terminal circuit, and the amount of maximum power that can be transferred to the load is VTH square over 4 RTH. Now, we also want to know how the load voltage and load current will vary as we vary the load resistance from 0 to infinity. When RL is 0, the load is a short circuit. The voltage across the short circuit is 0. So, VL will be 0 when RL is equal to 0. When RL is infinity, under open circuit condition, the load voltage will be VOC or VTH. So, Load voltage will start from 0 and reach the highest value VOC when RL is infinity or when load is open circuit. So graphically, we can show VL in this manner. VL increases from 0 and eventually gets saturated at VOC, which is also equal to VTH. Next, we want to know how the load current varies as we vary RL. When RL is 0, that means under short circuit condition, the load current is maximum and is equal to the short circuit current. The short circuit current happens to be the Norton's current. So under short circuit load condition, the load current will be maximum at ISC. And as we increase the load resistance, the load current will decrease. And when we have RL equal to infinity or open circuit load condition, IL will become 0. So the variation can be graphically shown in this way. For RL 0, the current is ISC and the current decreases monotonically and becomes 0 when RL is infinity. So it is important to understand the variation of these three graphs because that tells us many stories about the transfer of electric power. Now we'll look at the solution of an example problem on maximum power transfer theorem. In this circuit, R is our load resistance and we want to find out what is the maximum power that can be delivered to R. Here R is not fixed. We can vary R from 0 to infinity and set it at any desired value to get the maximum power. So R is the load and the load is connected between node A and B. The rest of the circuit between node A and B is our two-terminal circuit. To find the maximum power, we need to know VTH of the two-terminal circuit and RTH of the two-terminal circuit. So let me show the two-terminal circuit. This is open circuit condition. The voltage between node A and B, we call it VOC, and remember that this VOC is equal to VTH. We want to find VTH. There are many different techniques to solve this circuit. I will try to identify the physical features of this circuit and solve by using such simplifications. First, we observe that this 2 ohms resistance is in series with an open circuit. So this 2 ohms is ineffective. If this 2 ohms is ineffective, there is no current flowing through 2 ohms and there is no voltage occurring across 2 ohms. So this VOC voltage between node A and node B actually appears across 12 ohms resistance. If this 2 ohms resistance is neglected, this is simply a series circuit. We can find out VOC using voltage divider rule. Using voltage divider rule, we can see that VOC or VTH is equal to 24 volts. I have written here VTH because VOC and VTH are the same. Next, we want to find RTH of this two-terminal circuit between node A and node B. This circuit does not contain any dependent source. It has only independent sources. So we can apply case 1. According to case 1, we deactivate all independent sources in the circuit and we find the equivalent resistance. There is only one independent source, which is a voltage source. To deactivate it, we will replace it by a short circuit. So this is what we get, and RTH is the equivalent resistance between node A and node B. This is a very simple resistive network. We can easily say that this 4 ohms and 12 ohms are in parallel and the parallel combination is in series with 2 ohms. So RTH is 12 and 4 ohms in parallel, 2 ohms is in series. So we get RTH is equal to 5 ohms. Now that we know VTH and RTH, using maximum power transfer theorem, we can easily calculate the maximum power which can be transferred or delivered to R. The relationship is PL max is VTH square by 4 RTH. If we do the calculation, we find out that the maximum power that this two-terminal circuit can deliver to R is 28.8 watt. So in today's class, we have discussed Norton's theorem and maximum power transfer theorem. I did not solve any problem on Norton's theorem today because if you know how to solve Thevenin's theorem related circuits, you should be able to solve Norton's related problems without any additional difficulty. But in the lecture, in the class, during the interactive session, we will solve problems on Norton's theorem. Thank you. That's all for today.